When we think of robots, we usually picture something strong, maybe a little rigid. But what happens when that strength needs to be, well, gentle? Today, we're going to dive into a breakthrough that could give robots a sense of touch they've never had before, and it could change everything from surgery to how we pick our fruit.
I mean, think about it. How do you get a robot to pick a raspberry? It sounds simple, right? But teaching a machine the difference between a firm grip and a crushing one is a huge challenge in robotics. If you get it wrong, you've got raspberry jam. Or in a more serious setting, a really big problem.
And see, that's the core issue. Most robots are built for pure, brute strength. Their grippers, they're fantastic for building cars on an assembly line. But ask them to handle something fragile, like a piece of electronics, or even human tissue, and they're just all thumbs. They have all the power, but absolutely no finesse.
So if you're an engineer, where do you look for an answer? Well, you look to the best designer there is, nature. And that's what led to this incredible field called soft robotics, where robots are built from flexible, squishy materials that can bend and move a lot more like living things.
The inspiration is literally all around us. I mean, take an octopus. Its arms can curl and grip with this amazing dexterity, and they don't have a single bone in them. Scientists have been trying to copy that incredible, adaptable movement in machines for a while now.
But okay, how do you actually get these soft materials to move? The usual methods are, well, they're a bit clunky. You can pump them full of air, you can pull on them with tiny cables like a puppet, or you can zap them with voltage. These all work, sure, but they have their limits. And researchers at IIT Hyderabad thought, there's got to be a more elegant way to do this. And that brings us to their, well, shocking new idea. The real innovation here is this beautifully elegant concept that combines the ability to move and the ability to feel into a single material. So here's the question that changes the whole game. What if you had a material that could make its own electricity just by being bent? A material that bends when you apply electricity, but also creates its own electrical signal when it's bent by something else. That two-way street, that communication, that's the secret sauce right there.
This amazing property has a name, Flexoelectricity. The easiest way to think about it is like a smart sponge. If you squeeze it, it creates a little voltage, and if you apply a voltage to it, it squeezes itself. This is the key that researchers are about to put to work in a very, very clever way.
And what's that job? Well, it's to be the heart of a brand new kind of robotic gripper. So, let's meet the star of our show, the FlexoGrip.
What's so brilliant about this is how simple the design looks. These two little fingers are made of that special flexoelectric material we just talked about. This means the gripper doesn't just grab an object, it simultaneously feels how hard it's grabbing. It's a gripper and a sensor all in one.
This dual ability, this gripping and sensing at the same time, is what makes the FlexoGrip so special. It's not just a hand, it's more like a hand with nerves. Let's dig into how it actually works in its two different modes.
Okay, let's break this down because it's kind of like having two superpowers in one device. First, you have open circuit mode. In this mode, the gripper is a pure sensor. As it bends around something, it generates an electric signal. That signal is real-time feedback that tells you exactly how much force is being applied. Then, you flick a switch to closed circuit mode, and it becomes an actuator. You apply a specific voltage, and the gripper bends to a precise degree. You're telling it how hard to squeeze, so it can feel and it can act.
Now, having those two modes is awesome, but it's not enough on its own. To be truly useful, the system has to be predictable. You need to know, without a doubt, that a certain amount of voltage will create the exact right amount of grip for whatever you're trying to pick up.
So, the researchers did their homework. They mapped it all out. Now, this chart looks pretty technical, but the takeaway is actually really simple. They figured out the exact conditions needed for a successful grip. See that purple area? That's where the grip fails. Either it drops the object or crushes it. But that green area? That's the sweet spot. It's a predictable roadmap for how to hold on securely.
And their analysis boiled down to a few clear rules. First, it's totally predictable. More voltage equals a stronger grip. Simple. Second, they found that giving the gripper a slight precurve actually improves its performance. But the bottom line is this: it's not guesswork anymore. They've created a reliable, controllable system that does what you tell it to do.
Okay, so we've got a smart, gentle, and really predictable robot gripper. But so what? Why does this matter? What does this cool new invention actually mean for the real world?
Well, this is so much more than just a neat lab experiment. This research gives us a direct path to building robots that can interact with the delicate world around us in a whole new, much smarter way.
Let's just dream for a second. In medicine, imagine a surgical tool that can actually feel tissue and apply just enough pressure and not a bit more. Or in farming, robots that could harvest soft fruits like berries without ever bruising them. And in manufacturing, they could assemble tiny, fragile electronics with a touch that's basically human.
And really, that's the big question this research leaves us with. This isn't just about building a better robot hand. It's about creating a whole new generation of robots that can feel, adapt, and interact with our world. It's a huge step towards machines that can truly work with us, not just for us, in our most delicate tasks. The only question now is, what are we going to build with them next?